Hey, Co-21C students. Here is a video in lieu of having class on Friday, May 5th and Monday, May 8th. I'm pretty much going to cover just more kind of vector stuff. So have a watch. Last time we were talking about projecting a vector onto another vector. So I'm going to kind of re-go over that and then kind of follow up. So we have the following kind of situation. This is your vector u, and this is your vector v, and the angle between them is theta. And if you drop down v, or if you drop perpendicular u onto v, this vector here, that vector is the projection of u onto v. And this vector here is the orthogonal complement of u onto v, which we did not talk about last time. That vector, that angle is 90 degrees. And so when we talked about finding the projection, we first talked about finding the length of the projection. I'll just point out that the length or magnitude of the projection of u onto v is also called the component of u onto v. I didn't make up these names. I don't know why it's called that. But the way we find that is we say, well, that length is going to be, well, I should say, actually back up, I say cosine of theta is going to be the length of that projection. So the component, and we did do this part last time, but I thought it'd be good to see again. The component of u onto v over the magnitude of u. And then what we typically do when we see a cosine is we try and make a dot product appear. So I'm going to multiply both sides by both the magnitude of u and the magnitude of v. So the magnitude of u and the magnitude of v. So then this left-hand side, well, the magnitude of u times the magnitude of v times cosine of theta, the angle between them, is just u dot v. And over here, the magnitudes of u cancel, and you get the component of u onto v multiplied by the magnitude of v. So then the length of this vector here, the component of u onto v, is just u dot v divided by the magnitude of v. So the magnitude of the projection of u onto v, which again is just the component. Again, I really don't know why we use this name. I don't particularly love it, but it is what it is. It's just u dot v divided by the magnitude of v. And then to find the actual vector, well, the vector is a magnitude times a direction, or a length times a direction. So we're going to take this length of this vector and multiply it by the direction of this vector, but this vector is in the same direction as v. So the direction of this projection of u onto v is just the vector v divided by its own magnitude. And so then, I guess I should circle some things here. So we got this, cool, yeah. And then the projection of u onto v is just equal to this times this, the magnitude times the direction. So it's the component of u onto v times the direction, v over magnitude of v. And there's a couple ways of writing this. You can write it as literally just u dot v over the magnitude of v times v times, it's not a dot product, that's times v over the magnitude of v. But the people usually write it as either u dot v over the magnitude of v squared times the vector v, or u dot v over v dot v times the vector v. I often like to put this part in parentheses just to kind of remind myself that's a scalar. That's the scalar times the vector, scalar times the vector. And then the orthogonal complement, well, the projection plus the orthogonal complement is equal to the vector u. So since the orthogonal complement of u onto v plus the projection of u onto v is equal to u, we can say that the orthogonal complement of u onto v is just equal to u minus the projection of u onto v. Let me think it's a little this here. Here's the projection. I like writing it this way personally. View onto V. Yeah. So let's look at some examples of this. I'll put the papers down. Put this chair over here. So yeah, spot to put the papers down. I'll definitely upload these notes as well, so you can look at them without having to like listen to all this if you prefer. So let's say we're going to let U equal I plus 3j and V equal to 5I plus 2j. And let's find all the things, the component, the projection, and the orthogonal complement of U onto V. And you don't have to draw these to be able to see them, but it's kind of nice to see what they look like. Let's do some colors here. So let's say U is the vector. So we're going to go over 1 up 3, 4, 5. Cool. So here's the vector U over 1 up 3. There's U. And the vector V is over 5 and up 2. So we'll do 5, 1, 2. Go like that. And the projection of U onto V is going to look like, well, we're dropping U onto V perpendicularly. So it's going to look something like this. So right here, there's your projection of U onto V. Cool. So the component of U onto V, I'll point out, I often end up recreating this formula every time I use it because I just don't remember it. But since we just did it, I know it's going to equal U dot V divided by the magnitude of V. So that's just going to be U dot V is going to be 1 times 5 plus 3 times 2, right? Just multiplying the components, like components together, divided by the magnitude of V, which is going to be the square root of 5 squared plus 2 squared. So that's going to equal 5 plus 6, which is 11, over the square root of 29. So the length of this vector here is 11 over the square root of 29. And then the actual projection of U onto V is just that magnitude, that component of U onto V times V divided by the magnitude of V. So that's going to end up equaling, well, that's 11 over root 29. And the vector V divided by the magnitude is just going to be 5I plus 2j over the square root of 29. Now, I probably wouldn't leave it like that. I would probably actually write it as, I would distribute that 11 to each of those things and write it as 55I plus 22j over 29, or even probably more likely 55 over 29I plus 22 over 29j. And then finally, and one reason for writing this is because it makes it easier to find the orthogonal complement as well. So the orthogonal complement of U onto V is just, well, again, I'm thinking of the projection plus the orthogonal complement equal to U. So U minus the projection is going to be what we're looking for, which is just going to equal, so U is I plus 3j minus the projection, which is 55 over 29I plus 22 over 29j. So let's see, 1 minus 55 over 20. Okay, so 29 over 29 minus 55 over 29 is negative 26 over 29I. And 3 times 29, well, 3 times 30 is 90. So 3 times 29 is 87. So 87 plus 22 is going to be 109. Oh, sorry, 87 minus 22 is going to be 65 over 29j. And that looks right. This vector here, which is the orthogonal complement of U onto V, definitely looks like it's going left. So it's a negative I component, and up, so a positive j component. That looks right here. I guess I could label this one. Yeah, this is the projection. Cool. So a more important thing to think about here is, why might this be useful? So why might this be useful? Well, in a little bit here, not in this video, I don't think, But in a couple classes, we're going to start talking about finding the distance between like a point and a line, or a point and a plane, and being able to find the orthogonal complement kind of between the line and the point, or the point and the plane and the point, is what's going to allow us to find the distance. So for example, we might say, let's find the distance from the point 1, 3 to the line y equal to 2/5 x. Well, it's really just asking the same thing we did before. So here's the line y equals 2/5 x, which goes over 5 and up 2. And here's the point 1, 3. Now, when you're finding the distance from a point to a line, you're finding the distance from the point to the closest point of the line, aka the distance that'll be essentially perpendicular. So it's like you're dropping a perpendicular from that point onto the line, and you're trying to find this distance here. But this distance is exactly the distance you would get if you drew some vector from the line, and we'll pick the origin, although you don't actually have to pick the origin. You can pick this point over here, but drew a vector emanating from a point on the line to the point in space and said, okay, that vector is u. The line also has a vector associated with it, right? The vector that this line goes through is the vector that's over 5 and up 2. So this vector is the vector 2i plus 5j. The vector from 0, 0 to 1, 3 is the vector I plus 3j. If I want to find that distance really is just equal to the magnitude of your orthogonal complement, which we just found in the previous page. Let me go look back. That was gross. It was, so that's in the magnitude of negative 26 over 29i. Ooh, no, that's actually not helpful. I thought I had something helpful. It's not that helpful. Plus I plus 65 over 29j, which is just going to equal the square root of negative 26 over 29 squared plus 65 over 29 squared. And I wouldn't do anything else with that, but that would be your distance between this line and that point. And so that's definitely an idea we're going to use later on. Yeah, so that's about it as far as things we like to do with the dot product. We have we talked about the projection and the orthogonal complement. Before we talked about how you find the angle between two vectors, and also specifically we talked about how if the dot product is 0, then the angle between the two vectors is 90 degrees, or in other words, perpendicular vectors have a 0 dot product. So let's remind ourselves. So I'm kind of on to a new section now, so I'll just I'm still following my format here. So we just learned recently that the dot product, also called the scalar product, because when you dot two vectors together, you get a scalar output. Again, one more time, u v theta, doesn't matter which way we write u and v, the dot product's the same either way. U dot v is equal to the magnitude of u times the magnitude of v times cosine of theta. Also, additionally, if you write u and v in the component forms, like u equal to, you can either write it as, say, like a, b, c, or if you prefer, a times the unit vector I plus b times the unit vector j plus c times the unit vector k. And similarly, if v is, say, equal to, let's call this a1, b1, c1. And let's say that v is a2, b2, c2, or a2i plus b2j plus c2k, then u dot v is equal to the like components multiplied together and added up. So a1 times a2 plus b1 times b2 plus c1 times c2. technically this is true no matter how many dimensions or components your vectors have. So although in this class we'll mainly focus on just vectors with 2 or 3 components, because those make some physical sense that you can have vectors in 2 or 3 dimensions. You can actually have vectors of any dimension. So you can have a 4th dimensional vector, 5th dimensional vector, et cetera, and you'll definitely see more of that when you take like linear algebra, when we talk about systems of equations with more than 3 variables. So yes, notably, u dot v is equal to 0 if and only if u and v are perpendicular. Very, very true. So let's look at it now. We want to explore this kind of question. Do I have enough room here? I might. So we want to find a vector perpendicular to u equal to 5i minus 2j plus 3k. Now, if you think about it, in 3 dimensions, there's going to be a lot of potential vectors that are perpendicular to u. In fact, more than a lot, an infinite amount. Right? If you've got some vector u looking like this, well, if you think about the plane that it is perpendicular to, then any vector in this plane will be perpendicular. For example, this vector going this way, certainly perpendicular to u. So is the vector like coming out like that way. That vector is perpendicular. And really any vector that sits in this plane is perpendicular to u. We can come up with a lot of things. For example, v1 could be, I don't know, 4i minus 5j minus 10k. If you dot those together, u dotted with v1 is equal to 5 times 4 minus plus negative 2 times negative 5 is 10, and then 3 plus 3 times negative 10 is minus 30. Yep, that's 0. Or you could find another one. I don't know. You can make up something silly like, I would say 2i plus 5j plus 0k. And then u dot v2 is 10 minus 10 plus 0, which is 0. And you could go on and on and on like this. So, yeah. So just to kind of reemphasize here, perpendicular vectors have a 0 dot product, and vectors that have a 0 dot product are perpendicular. But now we're going to talk about the cross product, also called the vector product, because when you cross 2 vectors together, you end up getting another vector. So u cross v can be defined to be equal to the magnitude of u times the magnitude of v times sine of theta times the vector n, where n is a unit vector that is perpendicular to both u and v. And I should say, as determined by the right-hand rule. So when we say the right-hand rule, what we mean is when when you're crossing 2 vectors here, u cross v, the result will point in, well, if you put your, so let me just draw a picture. So if u is going, say, like this direction, and v is going this direction, let's say they sit like in the xy plane. So here's u, here's v. If you put your fingers along u, sorry, this is not great, and curl them towards v, your thumb should point in the direction of the cross product. So the direction here would be kind of like, so let's say these both live in this plane here, then here is n shooting out of the plane that is perpendicular to both u, or where n is perpendicular to u cross v. Now I'll point out, if we switch this around, so we have like, say, like, now we have v here, and u. I should have just changed the order. Oh well. Let's say this is still u and this is still v. Yeah, that's good. They're still both in the plane. But now if we do v cross u, when I put your fingers along v, but you curl them towards you have to turn your hand over to curl them back towards you, and your thumb kind of points down. So here, that's where your n vector is pointing. Still perpendicular to the vector is pointing in the opposite direction. So interestingly enough, when you cross two vectors together, the order actually does matter. U cross v and v cross u produce vectors that point in opposite directions. Literally opposite. Actually, so if you said I know u cross v is this vector, v cross u would just be the negative of that vector. A couple of good things to know. So if you think about like your three-dimensional coordinate system, right, where this is x, y, and z. So if this is the unit vector in the x direction, that's I. Here's the unit vector in the y direction, it's j. Let me get a different color pen for you. Do I have a black pen around here? We got a black pen real quick. All right, 1 second. And the unit vector of length 1 in the z direction is k. Well, it is definitely true that I cross j is equal to k. And this seems like a time where we should put arrows on these, right? Because right-hand rule, take this one, turn your fingers towards that j, and then your thumb will point in the k direction. And it's also true that j cross k. So again, fingers along j, curl towards k, thumb points in the I direction. And k cross I is equal to j. Put your fingers vertically up, curl them outward towards the x direction, and your thumb will point in the positive y direction. And then if you turn them around, they actually do the opposite thing. So if you do like say j cross, I should say not turn around. If you interchange the order of cross producting, j cross I is going to be negative k. And k cross j is going to be negative I. And I cross k, sorry, I tried to put an arrow there. I cross k, there's no little arrow there, sorry, is equal to negative j. And then any vector crossed with itself is going to be 0. So just for example, I cross I is going to be 0, because if you look back here, the cross product of two vectors is equal to the magnitude of the first vector times the magnitude of the second vector times sine of the angle between them. But the angle between a vector that and itself is 0, and sine of 0 is 0. So this whole thing is 0. Sure. So let's look at some examples. Let's say I want to find, let u equal I plus 3j and v equal 5i plus 2j, the same vectors we were looking at before. So both u and v are in the xy plane. To get a vector that is perpendicular to both of them, it'll have to point outward of the xy plane in the z or the k direction. So yeah, let me write that down. Because u and v are both in the xy plane, their cross product, u cross v, will point in the k direction, or maybe the negative k direction, so that it's perpendicular to both u and v. So how do we calculate the cross product? Well, there's a couple ways of doing it. Here's kind of the most annoying way. U cross v, you can actually literally just FOIL it out. You can say, well, it's I plus 3j cross 5i plus 2j. And then you can literally cross each part together. So you can say, okay, it's going to be I cross 5I. Yeah. Plus I cross 2J plus 3J cross 5I plus 3J cross 2J. The constants don't really matter. So I cross 5I is the same as 5 times I cross I, and this is going to be 2 times I cross J. This is going to be 3 times 5, so 15 J cross I. This is going to be 6 J cross J. We know that J cross J is going to be 0. We know that I cross I is going to be 0. So we're left with 2I cross J, but I cross J was K. I always think of it as kind of the order of the letters. If it's in order, it kind of is positive. So I cross J goes to K, J cross K goes to I, and then K circle back around to I, K cross I equals J. So I cross J is K, and J cross I is negative K. So we end up getting negative 13K as our cross product of these two vectors. Okay, it's kind of cool. It's annoying to do this for any vectors. Let me show you another example, and then we'll talk about how it can be less terrible. So let's say our vectors were 2I minus 3J plus 4K, and V is I minus 2J plus K. Okay, so if I want to do U cross V, it's going to be terrible. So U cross V is going to be 2I minus 3J plus 4K cross I minus 2J plus K. So you have to do all 9 pairs of the things. So it's going to be, I'm going to factor out the constant. So I'm going to get 2I cross I plus 2 times negative 2 is negative 4I cross J plus, let's see, 2 times 1 is 2I cross K plus, let's go down to another row. So let's see, then I'm going to do negative 3 times 1. So negative 3 J cross I. Oh boy. Plus negative 3 times negative 2. So positive 6 J cross J. And then finally this with this, I get minus 3 J cross K. Plus now I'm doing the 4K one. So 4K with I is going to be 4K cross I, and then 4K times negative 2, so negative 8K cross J. And then finally, 4K cross K. Gross. That's 0. That's 0. That's 0. And I end up getting, let's see, so I cross J is K, so I get negative 4K. I cross K is negative J. So I'm going to get, minus 2J. I should double check that, I cross K is, negative J. Good. Okay, I thought so, I was only sure. And then we know that I cross J is K, so J cross I is negative K, so I get plus 3K. And then J cross K is I, so minus 3I. Oh boy. And then finally, K cross I is, right, J, so plus 4J. And then K cross J, well, I know J cross K is I, so K cross J is negative I, so plus 8I. So let's see, negative 4K plus 3K is minus K, I'll put at the end. Negative 2J plus 4J is 2J, and then negative 3I plus 8I is 5I. Usually we write it in order IJK. Okay, that was terrible. There are at least 2 other good ways of doing this. So here's one way. Well, actually, they're the same way, but there's different ways. So to find U cross V, you can find it as the determinant of the matrix number path, right? So this is the determinant method. Interesting to know, whereas you can take the dot product of vectors up to any size, The cross product is actually only defined for vectors as big as being in 3 dimensions. You can't do the cross product for vectors in 4, or I don't think there's a way that the cross product is defined for larger vectors in higher dimensions. So U cross V is going to be the determinant of the following 3 by 3 matrix. The first row, you're just going to put the unit vectors I, J, and K. In the second row, you're going to put the first vector. So U is the vector 2I minus 3J plus 4K, but just 2I just the coefficient, sorry, just 2. We don't actually need the I, J, and K, minus 3 and 4. And then here we're going to get the components of V, which will be 1, minus 2, and 1. And now there are 2 ways of taking this determinant. One way is what's called cofactor expansion, where you look at this component, I, and you cross out the row and column it's in, and then you multiply it by the determinant of what's left. So this is going to equal I times the determinant of the remaining 2 by 2 matrix, which is -3, 4, -2, 1. And then you alternate signs. So then you look at this entry, you cross out the row and column, and what's left is 2, 4, 1, 1. So it's going to be minus J times the determinant of 2, 4, 1, 1. And then it's going to be plus K. It's always alternating signs. So you do cross out that, and you get 2, -3, 1, -2. And then, in case you didn't already know, the determinant of a 2 by 2 matrix, A, B, C, D, like that, is the product of the diagonal elements minus the product of the off diagonal elements. So AD minus BC. So here, calculating this, we're going to get I times -3 minus -8. We're going to get minus J times 2 minus 4. And we're going to get plus K times -4 minus -3. Which ends up being -3 plus 8 is 5I. -J times -2 is plus 2J. And K times -4 plus 3 is minus K. Same answer. There is another way of doing this, which is still the same work. It just looks a little different. Let me show you that too. So you could also do it the following. You can write down I, J, K, and their columns there. Sorry, rows there. And then what you can do is you can actually repeat either the first 2 columns next to it or the first 2 rows under it. Either way works. I'm going to do the first 2 columns. I'm going to have I, 2, 1 again, J, -3, -2 again. And what people do is they do all of these multiplied together. So this, this, and this. So I'm going to get I times -3 times 1 plus J times 4 times 1 plus K times 2 times -2 minus this, this, this. So minus K times -3 times 1 minus I times 4 times -2 minus J times 2 times 1. And it should work out to be the same. Let's see. I've got -3I minus -8I. So 8I minus 3I is, yep, 5I. And then I've got 4J minus 2J. So 2J. And I've got -4K plus 3K, which is minus K. Yep, same thing. So either way works. This is the method I usually tend to prefer, but you can use whatever you like. Ooh, so my neck's a little sore from looking down so much. Ooh, okay. So let's look at one. And I think that's enough examples. Oh yeah, let's talk about this. This is kind of fun. So let's find a vector perpendicular to the plane x plus 2y plus 3z equal to 6. Okay, so let's draw some pictures here. That's a little bigger than I meant to be, but it's fine. So let's see. So you can get x equal to 6 as your intercept, and y equal to 3, and z equal to 2. Man, I made me z. I got a little ambitious with my z-axis there. So here's my plane. Let's put it in green. And can I make the points meet up? Maybe. And I want to find a vector that is perpendicular to that, which we usually call n for the normal vector. Normal is another word we use kind of interchangeably with perpendicular. Orthogonal, also a word that we use interchangeably with perpendicular. So what I can do is I can find any two vectors in this plane and then take their cross product to get the vector n, or at least a vector n. So let's see. I'm going to make it different. I'm going to make different choices than Grant made. Because I'm just using Grant's notes, by the way, in case you didn't know. So here's a vector in the plane. It's starting at the point 0, 0, 2 and ending at the point 6, 0, 0. So one vector, let's call it v. V is the vector, well, 6 minus 0, 0 minus 0, and 0 minus 2. Or if you prefer, 6i minus 2k. And then let's say this is my vector u. Oops, wow, can I draw? So that's my vector u. And that's starting at 0, 0, 2 and ending at 0, 3, 0. So u is the vector 0 minus 0, 3 minus 0, 0 minus 2, or 3j minus 2k. So then to find u cross v or v cross u, either way is fine. I'm going to actually do v cross u because that's going to point out that way. I mean, it doesn't really matter which way it points, but v cross u is going to be I, j, k, and then the vector v, so 6, 0, negative 2, and then the vector u, 0, 3, negative 2. And when I do this, I'm going to get I times the determinant of 0, negative 2, 3, negative 2, minus j times the determinant of 6, negative 2, 0, negative 2, plus k times the determinant of 6, 0, 0, 3. And that's going to equal, let's see, 0 minus 6, so 6i, minus j times negative 12 times, or sorry, negative 12 minus 0. And then finally, k is plus k times 18 minus 0, which is equal to 6i plus 12j plus 18k. Now, here's a fun fact that is always true. That vector points that way, but so does any multiple of that vector. So specifically, if you take this vector and you multiply it by any number, it's still in the same direction. I'm going to multiply by 1/6. So check this out. 1/6 n is equal to, well, just I plus 2j plus 3k. So this vector, I plus 2j plus 3k, or if you prefer, 1, 2, 3, is perpendicular or normal to the plane x plus 2y plus 3z equal to 6. And it's not a coincidence that the components of this vector match the coefficients of x, y, and z. It is actually always true that if you're trying to find a vector perpendicular to a plane, you can just take the coefficients of x, y, and z, and those can be the components of your normal vector. Kind of great. The reason behind this is because of the following. Yeah, I'll just do it this way. So let's say I want to find a vector perpendicular to the plane 5x minus 17y plus 9z equal to 1. I know the answer, or an answer, is going to be 5 negative 17, or 5i minus 17j plus 9k. There's a couple ways to do it, but I'm going to say the answer is 5i minus 17j plus 9k. I'll point out that sometimes people are very specific about what they want in a normal vector, and they might say it needs to be a unit vector. So then you can say, or n could be the unit vector 5i minus 17j plus 9k, all divided by the square root of 5 squared plus negative 17 squared plus 9 squared, which would end up being, let's see, 17 squared is 289, 9 squared is 81. So add this together and you get 290 plus 80, which is 370, and 5 squared is 25, so 395. So you could write this, although it feels kind of dumb, as 5 over the square root of 395i minus 17 over the square root of 395j plus 9 over the square root of 395k. And it's only really important if they say they want a direction vector, meaning they want a unit vector. So here's how we do this. Oh yeah, there's a couple ways of doing this. It's kind of cool, but let me show you the kind of thought process behind why this really works. So the whole idea here is that here's our plane. And we can pick some point in the plane. If I let, yeah, interesting choices here. Okay, sure. I was talking about how we find this. So let's pick a, let's say we have, how do we, sorry, I have to think about this for 1 second here. If I want to find, oh yeah, sure. Yeah, sorry, I'm thinking backwards. So new question, kind of going the other direction. We want to find, sorry, I got kind of off track there. We want to find a plane containing the point 0 to -1, normal to the vector, or perpendicular to the vector 3i minus 2j minus k. So here's our point, 0 to -1. And here is the vector perpendicular sticking out of it, 3i minus 2j minus k. And what we're going to do is we're going to say, well, any other, let's say I want to describe any point in the plane, x, y, z. Because that's really, when you're writing this equation, that equation is describing any point in the plane, just like the equation of a line describes any point on a line. But notably, this vector from that point to that point is in the plane, meaning the vector from 0 to -1 to x, y, z is perpendicular to the vector 3i minus 2j minus k. So let's call this vector v. V is equal to the vector x minus 0, comma, y minus 2, comma, z minus -1. Or if you prefer, xi plus y minus 2j plus z plus 1k. And it is true that since v and, sorry, I didn't label this, n are perpendicular, their dot product must be 0. We'll check this out. Let's do it this way. N dot v is equal to, well, n is 3i minus 2j minus k, and v is xi plus y minus 2j plus z plus 1k. When I dot these together, I multiply the like coefficients, so you get 3 times x minus 2 times y minus 2 plus -1 times z plus 1 equal to 0. Or multiplying it up, making it look a little bit nicer, you get 3x minus 2y plus 4 minus z minus 1 equal to 0, or 3x minus 2y minus z plus 3 comes to the other side is equal to -3. And notably, not surprisingly, the coefficients of x, y, and z are exactly the components of the I, j, and k parts of that vector. Now, the easier way to do this is to just say the following. We're going to say, well, great, I know those coefficients, or sorry, those components are the coefficients, so I know the equation of the plane has to be 3x minus 2y minus z equals to some constant. And then we're going to plug in the point that's in the plane. So we know that 3 times 0 minus 2 times 2 minus -1 equals d. So that's -4 plus 1. So d equals -3. Just like we had over there. Oh, yeah. So we end up getting exactly 3x minus 2y minus z equals -3. Sure. I'll talk about 2 more things. Yeah, 2 more things. Or is that a good stopping place? Yeah. Yeah, I'll talk about two more things and then I'll stop. What time is it? How much time have I been videoing here? I cannot see how much time I've been videoing here. Let's see. I'm just curious. Does it not show? I wonder if I'm gonna stop sharing for just a second just so I can see. I feel like there's a timer there sometime, but I guess not. How annoying. Anyway, let me continue to share. I'm almost done. So the last thing I want to talk about is just a couple of interesting facts that sometimes come up. The area of a parallelogram. So if this is your parallelogram, well, we can think of this side as being a vector, and this side as being a vector, and this side as being the angle between them. Well, if we know what this height is here, and we call this the base, well, then that's just like a rectangle, and the area is just equal to the base times the height. Let's give our vector some names. Let's call this vector u. Let's call this vector v. So the base is really just the magnitude of v. And the height, well, I need to use a trig function. I'm going to say that sine of theta is equal to the opposite side, which is the height, divided by the hypotenuse side, which is the magnitude of u. So that's going to equal, or h is going to equal the magnitude of u times sine of theta. So that's going to be the magnitude of u times sine of theta. Oh, but when you have the magnitude of v times sine, magnitude of v times sine of theta, that's exactly equal to the magnitude of the cross product. So this is exactly equal to the magnitude of v cross u or u cross v, whichever way you want to do it. It doesn't matter, because when you take the magnitude, whether or not your cross product is pointing one way or the other, the magnitude of it will still be the same length. Right, the whole point is here, right? When you do the cross product of v and u, I'll just point out that v cross u is the magnitude of v times the magnitude of u times sine of theta times the vector n that is normal to u and v. But when you do the magnitude of all this, that's a unit vector. So the magnitude of all of this here is just a scalar, and the magnitude of the unit vector is just 1. So that's why you end up getting, oh, this is equal to just the magnitude of the cross product. And then we can also point out that the area, if you call this point A, this point C, and this point B, and you want to think about, say, like this triangle ABC, well, that triangle is half the area of the parallelogram. So triangle ABC, the area is equal to 1/2 the cross product, the magnitude of the cross product of u and v. Cool. And then lastly, we can talk about the volume of a parallel pipette, which is a little bit annoying, but it's fine. So let's say we have the following. Come on. There's also good pictures of this in your book. So let's say we want to find the volume of a parallel pipette. A parallel pipette is just like a 3-dimensional box, except it doesn't have to be right angles. It can be kind of slanty. So they have something like this. And then it kind of does this like that. Right, it doesn't look perfect, but you get the idea, right? And so what we're going to do is we're going to say, well, let's call this vector here u, and we'll call this vector back here v. Oh, sorry, v. And u and v are both in like kind of the flat plane, and then u cross v is going to point straight up. So here's u cross v, perpendicular to the plane, the XY plane essentially. And then let's call this vector here W. And we're actually going to look at the angle between W and U cross V. So let's say this for a minute. So the volume here is going to be the area of the base times the height. But as we saw previously, the area, the base is just like a parallelogram, and the area of a parallelogram is the magnitude of the cross product. So that's going to be the magnitude of U cross V. And then the height, well, let's see. If I want to find the height here, that height, well, if I take cosine of this angle, cosine of theta is equal to the adjacent side, which is the height, divided by the hypotenuse, which is the magnitude of W. So height times cosine theta, sorry, magnitude of W. Sorry, that looks terrible. I know, times cosine theta is equal to, let me write that again. The magnitude of W times cosine theta is equal to the height. But look, that looks like a dot product. You have the magnitude of something times the magnitude of something times cosine of the angle between them, right? Because here's your one something, U cross V, here's your other something. So this is really the dot product of this with that. This is really equal to U cross V dotted with W. The problem is, though, that sometimes when you do a dot product, things are in the wrong order, and the dot product ends up being negative, but a volume should always be positive. So we're going to slap some absolute values around it. And they are absolute values because U cross V is a vector, W is a vector, but then their dot product is a scalar. And this is called the triple scalar box product. Oh. So let's say, for example, we have the following. We have U equal to I minus J plus 2K, V equal to 3I plus 6K, and W equal to 2I minus 2J minus 3K. We would like to find the volume of the parallelepiped that they make up. So we're like, we've got U, V, and W. So first we're going to find U cross V. So U cross V is equal to, again, right, we write the I, J, K, then we're going to do 1, negative 1, 2, and then 3, 0, 6, but there is no J component there. And we're going to get I times the determinant of negative 1, 2, 0, 6, minus J times the determinant of 1, 2, 3, 6, plus K times the determinant of 1, negative 1, 3, 0. Which is going to be equaling, let's see, I times negative 6 minus J times 6 minus 6 is 0. So you actually get 0J. And then K times 0 minus 3 is plus 3K. Double check that if it looks right. And then we're going to do that dotted with W. So U cross V dotted with W is going to be negative 6I plus 3K dotted with 2I minus 2J minus 3K, which is going to equal negative 6 times 2 plus nothing times the negative 2 here. And then finally 3 times negative 3 is minus 9. That's negative 21, but then we have to slap absolute values around the whole thing. So 21. So the volume of the parallelepiped here would be 21. Alternatively, you can do this. It's kind of neat, I think. You can actually find the triple scalar product by just doing U, or I should say U, V, and W all there. And it doesn't really matter where you put them as long as you take the absolute value at the end. So we're going to put U, V, and W into our matrix that we're going to take the determinant of. So we're going to have U, so 1, negative 1, 2, and then 3, 0, 6, and then W is the vector 2, negative 2, negative 3. So instead of I, J, and K, we're going to get 1, negative 1, 2. So we're going to get 1 times the determinant of 0, 6, negative 2, negative 3, minus 1 times the determinant of 3, 6, 2, negative 3. plus 2 times the determinant of 3, 0, 2, negative 2. All right, so then we're going to get 0 minus negative 12. So 1 times 0 minus negative 12 plus 1 times negative 9 minus 12. Right, plus 2 times negative 6 minus 0, which ends up being 12 minus 21 minus 12, which is equal to negative 21. And then, of course, we need absolute values. So the volume is positive 21, just like it was here. Great. Have a lovely weekend. Please watch. Dumb to say watch the video now, because you've watched the video at this point if you've gotten this far. So I hope the video was helpful, and I will see you all on Wednesday. Take care.